Today, I will introduce the second section of this database storage to you. It's about the heap file structure, and some of the settings of the heap file structure, configuration, and an organization method, including a particularly typical which is used a lot in mainstream databases. That is, a log file storage. The main logics and some of the related operations of the log file system. Because CnosDB is also based on the log file storage of the log file store system. So we are going to elaborate on that as well. And today, we are going to talk about storage. This second lesson is storage 2. In the last lesson, we mainly carried out some basic concepts of data storage, including how to set up some basic structure of the storage on the hard disk. The outline of this section mainly includes 5 parts. First of all, this is a page-based storage structure. That is, how the page is stored in the database disk, and then its heap file. That is, the heap file of the heap structure of the heap in a number of ways, including the page layout. And then we will talk about the log structure, log file system. That is, log file system, how to work in the whole disk storage. Finally, we'll talk about its internal tuple structure, as well as in the tuple for the relational structure of some of the pre-processing. This is the main outline of today's session. Okay, about the page storage structure. In fact, the DBMS database management system, there are different ways to manage the corresponding pages in the disk, but also according to the sequence of the file organization to arrange the page. You can also keep the way, that is the heap sort of way, the organization of the file. And then we'll probably talk about hashing or index sequential access method, or ISAM. But today we'll explain how a DBMS manages the pages in a disk file by keeping the file organized. A heap file is primarily an organized collection of one page, and we can imagine this page as an ordered collection. Then the tuple is the tuples in a random order stored in this page. We want to support 2 operations. The first is that we can CGWD in the heap file system. That is, create, get, write, delete. Create and read or write or delete the corresponding page, CGWD. We talked about these page files in the previous lesson. Page is the basic structure in the disk storage, but also support traversal of all the pages. If it's a traversal to get all the pages, then the heap file needs to support that. Secondly, the heap part of the heap file needs to have some metadata to track which pages to exist. To find out the exact pages and which pages are still available in these pages, to find these available spaces and to get to these pages, and then to write the new tuple data to this page. Then it also needs this metadata to manage these pages and available space. The bulk is a heap file system to do some of the corresponding support operations. There are 2 main ways to implement a heap file. The first is the very familiar structure of a chain table. The header of the chain table structure has a pointer to a free page. That is to say, we say free in the free configuration list. One by one, the corresponding situation. I use a pen to draw this free page list. It is a record in the list of which page is still free pointer. And then the database is looking for a particular page. It needs this order to scan the page until this position is found. There's also a reserved page, a data page list, which is pages of data that have been used. This use list also keeps a pointer to the number of slots available for each page. That is, each page also defines how many of its own slots are available in the data, and then defines the slot. That is, records the slot, and then the free page list is a pointer to a completely empty page list that can be used. The free page list is completely empty pointer to a page that can be used. In the whole list, if our database finds a specific page, it will traverse in a sequential structure. First, find the first number 0. If not, then find the second number 1. In fact, it is relatively inefficient, so we will have a new way to optimize the operation. Then here comes the heap file operation. The corresponding operation of the page literal point of the heap file is that I use a dictionary to record the corresponding page. In the main database, I maintain a special page. This dictionary is actually a page. This special page stores the location of each data page. That is, each data page in which the corresponding position will be stored in it. For example, if part of this data page is free, then this directory keeps track of the number of slots that are available on each page and then makes sure that those records are synchronized with the data page. So when I go to do an insert, I can first find the page in the dictionary, and the dictionary also keeps track of how many slots are available on that page. So if I call that page space, I can write the tuple to that page. Once it's full, I will just request another space and direct the page. And that's how the dictionary in the heap file is used. So this is the heap file of the two ways to use. One is the chain table. The disadvantage of the chain table is that to find the page words how to do traversal of the way. Dictionary advantage is that it can guarantee synchronization without having to traverse to find the corresponding available page. And then again, in this page, for data phase, create, write, delete, insert, and other related operations. Okay, let's move on to the next page. First, we're entering a single page. How we handle the layout is actually quite simple. Each page is composed of a header and data. It follows a header data structure. For data layout, a common method is to track how many tuples are stored in a page. Every time an update occurs, each time a new tuple is stored, it is actually appended to the end. If a tuple is deleted, or if there are variable length attributes within the tuple, the entire page layout becomes invalid. Therefore, the header needs to contain metadata to keep track of things like the overall page size, whether the page is 4 kilobytes or 8 kilobytes. For example, it includes a checksum for verification and also its version, visibility and compression information of transactions, and self-content information. All these pieces of information are included in the metadata. The metadata organize this information accordingly. When setting up the data and configuring the tuples, There are two different layout methods. One is a slot page method, and the other is the lock structure method. This method helps address issues such as when a tuple is deleted or has variable length attribute, and gaps appear between tuples. This approach avoids the fragmentation issue, where, for instance, when I delete a tuple, the first slot is occupied, the second is empty, the third is empty, and the fourth is occupied again, resulting in significant fragmentation. So first, let's look at the slot page method. What is the slot page method? It's a slot array. This slot array maps the starting offset of tuples. The header record, it first has a header. In this header, it records the number of slots, the starting position of the last used slot, and a slot array that tracks the starting position of each slot. The slot array maps the starting offset of tuples. After mapping, what does it look like? The first slot array element 0 maps to tuple 1. The second slot array element 1 maps to tuple 2. When inserting a tuple, the tuple is inserted at the end of the page layout. The slot array is arranged from front to back 0, 1, 2, 3. The tuples 0, 1, 2, 3, 4 are inserted towards the end. When the slot array continues to insert 3, 4, 5, 6, the tuples keep getting inserted. When they meet, it indicates that the slot page is full. The entire page has been occupied. So it's a very good method for managing. When deleting, I just need to remove the slot array and the tuple. Then I can continue inserting until the header and the slot array and the number of tuples indicate that the page is full. This means that the page is fully occupied and the slot page is fully used. This is one method of page layout. However, today we are not focusing on the slot page method. Instead, we are talking about the lock system. How is the lock system implemented? How is the lock system generated? It actually has a very good and a long history. Around the early 1990s, people started to set this up. In the early 1990s, there was a relevant historical context. In the last session, I gave you an overview of the development of databases from the 1980s, and then into the 1990s and 2000. In the early 1990s, the performance of computer hardware began to grow explosively. The CPU speed became faster and faster. As you know, with the 486, 586 Penta, the CPU speed kept increasing according to Moore's law. Memory also became larger and larger. Although the sequential read speed of hard drive, as we discussed last time, for example, solid-state disks, and their read-write speed increased, the random read and write speed was still limited by physical seek time in mechanical hard drives and by garbage collection in solid-state drives. Thus, the time was significantly constrained. On the other hand, at that time, file systems like the Unix file system and FFS had a lot of random read and write operations. So the performance of random read-write, including reading from and writing to the hard drive, became a performance bottleneck for the entire system. Due to the presence of the page cache, early researchers of log file systems believed that random reads were not a major issue. With an increasingly larger memory, most operations could be cached. Therefore, the log file system aimed to reduce random writes to the hard drive, converting random writes into sequential writes. How do we reduce random writes? They use a very simple idea. They treat the entire disk as an append-only structure. It only appends data, continually adding to the end. This append-only log is always written sequentially. When we write new files, we append them sequentially at the end of the file. The log structure file system does not modify the original content. It appends the changes to the end of the disk. It only stores log records, not tuples in pages. For example, when we record log entries, we log database modifications. When I add a tuple to the storage, I record this insert in the log, such as ID equals to 1 and the value equals to 8. If I add another tuple or delete a tuple, I mark the tuple as deleted in the log. Similarly, for updates, I only include the modified attributes and the corresponding changes. Our CnosDB also uses log structure method. Essentially, it is a log file system. Logging helps address the issue of random writes by aggregating records in memory and sequentially writing them to the disk. The disk then stores incremental records. All data deletions and modifications are done through appending. This means that this records record modifications in an append-only manner, just like how we handle redo logs in databases. When using redo logs, we first record the log entries in the system, and then perform the actual commit log work. If the system fails, we can replay the redo logs to restore the system. This append-only approach to logging is a key idea in disk operations. So, in terms of the log structure file system, we can see that within the entire log file system, since we understand its great concept, which is to avoid any random write operations, and instead perform sequential writes, treating it like a log. In the log structure file system, the free space is managed using fixed-size segments. The hard drive is divided into fixed-size segments. Write operations are first written into memory, where they are serialized. After serialization, if the cache data in memory exceeds the size of segment, the log file system will write this data into free segment all at once. This means that I use memory buffers and perform sequential serialization. When the serialized data reaches the size of segment, the data is written into a free segment all at once. The benefit of this approach is that it reduces random writes and the frequent seek operations on the hard drive. This applies to both traditional hard drives and solid-state drives, reducing the frequency of command operations. By writing the data as a block, we reduce the interaction between memory and hard drive. This is also a resource-saving advantage of log structure file system. Additionally, in the log structure file system, how does reading operate? To read records, the log-based database management system, DBMS, scans the log backward and reconstruct the tuples. It needs to scan the log from back to front and build an index, allowing it to jump to the corresponding position in the log. The read records, it needs to reconstruct the log tuples. The benefit is that the write speed is fast. However, Considering the reading process, read speed is actually very slow. The append-only approach works well because the database doesn't roll back or redo or update the data. It continuously appends. To avoid slow read, we can build an index. The database can build an index to jump to the specific position in the log. And we can periodically compress the log by removing invalid operations. Periodically, we can compress the log to exclude invalid operations. If a tuple is updated, we can store only the inserted tuple. However, everyone knows that compression can lead to write amplification because it involves writing the same data repeatedly. To address this, we need to introduce operations such as garbage collection and other corresponding structures. Earlier, we mentioned that we allow indexing in the log file system. So how is indexing done? It is done like this. Within the segment, the contents of the log file are stored in the data blocks of the same size. For example, in the log file system, we compact segment with expired data blocks, forming new segment and deleting old data from the segment. How do we determine which data expired in log file system? At the beginning of each segment, a summary is created. This summary head stores the address of each data block in the segment. By comparing this address with the IMAP and inode index, if the addresses match, it is valid. If not, block is expired. Expired blocks are marked and compacted into a new segment, freeing up space and forming new segment. Thank you all very much. We hope to continue sailing in the vast sea of domestic database and make progress together. Welcome again. This is CnosDB. You can join our CnosDB Discord channel. And please sign up for the CnosDB Cloud as well. You can join that very easy in the cloud as well. Thank you. See you next time. Bye-bye.